Before we begin, two questions. Keep them in the back of your mind. First, if you could squeeze a crystal that a liquid grew all by itself, what exactly would push back? And second, how could you ever catch the exact instant it stops being solid? Hold on to those. Now, a picture you already know: water slides over a rock in a stream, and just downstream, a ripple stands still. A fixed ridge of raised water that holds its shape while the water pours straight through it. Look at what that is: a pattern that stays put, and a liquid that flows both at once, but there is a cheat. The rock is holding the ripple in place. Take the rock away, and the pattern washes out. So here is the natural conclusion, the tempting one: a flowing liquid can borrow a pattern, but it can never grow its own. A crystal needs something outside it to hold the ranks in line. Today, a liquid that breaks that rule, and the hard question of this whole film when it does, is that self-made crystal real? A true solid you could squeeze, or just a frozen ripple wearing a crystal's clothes? Let's build the two ideas we're about to fuse. First, a superfluid. Chill a gas of atoms to a whisker above absolute zero, and they stop acting like a crowd of separate particles. They lock into a single quantum wave, a Bose-Einstein condensate, sharing one phase across the entire cloud. That shared phase is what lets it flow with no friction at all. In the language of symmetry, the cloud has spontaneously picked one phase out of a whole circle of equal choices. We say it breaks U1 symmetry. Second, a crystal. Strip away the details, and a crystal is simply matter whose density repeats in space, peaks and troughs at a fixed spacing. Empty space looks the same wherever you stand. A crystal does not. It has chosen a set of positions. It breaks translational symmetry. Now, the tension, superfluid order says every atom is smeared coherently across the whole cloud. Crystal order says the atoms pile up at fixed sides. Those sound like flat opposites smeared everywhere versus pinned in place. And for decades, that is exactly why the word supersolid sounded like a contradiction. Supersolid refuses to choose. It breaks both symmetries at once, one cloud, the same atoms, carrying a rigid repeating pattern and perfect frictionless flow together. Two broken symmetries, two kinds of order, alive in one piece of matter, which leaves us exactly two jobs. How do you build such a thing? And how do you prove the crystal half is genuine? So how do you turn a plain condensate into a crystal? You hand its atoms a strange rule book for how energy depends on momentum. Normally, that relationship is a single ball, one lowest energy state, sitting at rest. Now cross two laser beams through the cloud, tuned so that flipping an atom between two internal spin states also hands it a kick of momentum. This is spin-orbit coupling. The atom's internal spin is welded to its motion. And it buckles that single ball into a double ball, two separate minima, a left well and a right well. Sitting at two opposite momenta, one knob, the strength of the laser coupling, which we'll call omega, sets how deep and how far apart those wells sit. Here's the move. The condensate has to choose: pour all the atoms into one well, and you get an ordinary uniform cloud, all drifting one way. But let them occupy both wells at once. And remember, this is one coherent quantum wave, so both means a true superposition, not two separate clouds sitting side by side, and the two momenta interfere. Two matter waves of opposite momentum, overlapping, make a standing ripple in the density bright, dark stripes, a crystal grown purely by interference, with a spacing set by the gap between the two wells. So take a moment. If the atoms truly sit in both wells at once, what should the cloud's density look like? And here's the thing: this is not a cartoon. That is a real image of the gas, actual stripes, spontaneously formed in the experiment we're following. Now let's turn the knob. As you raise the coupling omega, the two wells slide toward each other. And there is a beautiful way to picture the competition underneath. Treat the two wells as two miniature condensates, a left one and a right one, forced to share the same space. Two condensates will only interleave if they are miscible, if they would genuinely rather overlap than separate. Whether they do comes down to a contest of interactions: how hard atoms in the same well push apart against how hard atoms in opposite wells push. So here's your prediction to make. If we keep cranking omega higher and higher, what happens to the stripes? Here's the answer: crank omega too far. And the balance tips. The two condensates would rather not overlap. They demix. The gas dumps all its atoms into a single well, and the stripes vanish. The crystal dies at the critical coupling we'll call omega C. So the stripe phase doesn't live everywhere. It lives inside a dome, a finite window of coupling. And this is the catch that stalled the whole field for years. To get a strong, high-contrast stripe, you need atoms in opposite wells to barely interact compared to atoms in the same well in Rubin. The atom everyone reached for first, those interactions are nearly equal. So the stripes come out pathetically faint under 5% contrast, far too fragile to poke at. The Barcelona group switched to potassium-41, whose interactions you can dial with a magnetic field. A Feshbach resonance, and tuned the opposite, well, repulsion right down. The reward, stripes with up to 60% contrast. A supersolid finally robust enough to experiment on. Time to play the skeptic. We've made stripes, but is this really a crystal, or are we fooling ourselves? A good critic has two sharp objections, and we have to beat both. First objection, those stripes are nothing but an interference fringe painted by the lasers. The laser sets the spacing. So it is an imposed pattern, not something the gas chose. So quick commit, is the stripe spacing fixed by the laser's wavelength? Yes or no? Watch as the experiment changed omega. The stripe spacing changed with it from about 500 nanometers up past 650. While the laser never moved, the gas sets its own spacing. From the gap between its wells, the pattern is self-determined. Strike one against the skeptic's second objection, fine, but maybe it is still a rigid frozen ripple pinned lifeless. Then look again at that real image shot after shot. The stripes appear at a completely random position here, then shifted again, 350 runs. No preference at all. A pattern pinned by the lasers would land in the same place every single time. This one doesn't. The gas spontaneously chooses where to lay its crystal down, real honest. Broken translational symmetry, strike two. But the critic's deepest challenge is still standing, and it is the right one to ask. A true crystal isn't just a pattern in the right places. A true crystal is springy. Push on it, and it pushes back. It can carry sound. Does this one, that single question, can you actually squeeze it? Is what separates a real supersolid from a frozen imposter. So let's squeeze it. To test whether the crystal is springy, you shove it and watch. The experiment does exactly that. It suddenly changes omega, sharp kick to the stripes, and then fills the spacing over time. Now, if the stripes were a rigid frozen fringe, the spacing would just sit there, dead still. Instead, the spacing oscillates. It compresses and expands, compresses and expands. The crystal is breathing, so ask yourself what that breathing actually proves about the crystal. It proves the crystal is compressible, you can squeeze it and it springs back. And a compressible crystal carries a sound wave, a phonon. This is a stripe compression mode. And it is a definite fingerprint of a genuine full-fledged supersolid, the very thing that was missing and doubted. For years, in momentum language, it is gorgeous. The left and right wells slosh in and out of step. Their momentum gap widening and narrowing, which is precisely the stripe spacing breathing back in real space. Now, does the superfluid half survive all this? Here's the worry you should have if the atoms are flowing freely. Shouldn't the crystal just smear away? It doesn't, and that is the whole magic. Nudge the crystal sideways, and atoms quietly flow between the stripes to make up the difference. The lattice slides while the fluid counterflows. And the phase coherence never breaks. The gas even passes the textbook check for a superfluid. The ratio of its breathing to its sloshing frequency comes out at the square root of 5/2. Exactly what frictionless hydrodynamics demands, a crystal that springs back, a fluid that pours through it. Both at once now demonstrated. Now the reward, because near the edge of that dome, the breathing tells us something exact. Watch the compression frequency as we push omega up toward the critical point. So predict it first. As omega approaches omega C, where does the breathing frequency go? Here is what happens. The breathing gets slower and slower. The mode softens, its frequency sliding down towards zero, right? At the transition, the restoring springiness of the crystal runs out completely, a soft mode. And a crystal with no stiffness left is a crystal on the verge of melting. So the point where that frequency touches zero marks the exact coupling, where the supersolid gives way to an ordinary uniform cloud. For this gas, that critical point sits at the Raman coupling of about 2.05 recoil energies. And because the interactions behind it are set by a magnetic field, you can slide the whole transition wherever you like. Notice the cleverness of this. Instead of chasing the faint stripe contrast, which actually lies to you because leftover long-lived states keep a ghost of the pattern alive even past the transition. They located the melting point by listening for the node that goes silent, the mode that softens to nothing. So look back at our two questions. Squeeze the crystal, this liquid grew. What pushes back a real springy stiffness, the crystal zone? And near melting, that push goes soft. And how do you catch the instant it stops being solid? You listen for the node that goes silent, the breathing that slows to a stop. Two questions, both answered by one extraordinary gas. Here is a whole story in a single breath. A supercold gas, nudged by two cross lasers, grows its own crystal of stripes and still flows straight through it. Squeeze those stripes and they spring back, push the coupling toward the edge, and that spring goes soft and the crystal melts a solid and a liquid in one and the same breath to lock it in. Remember the word it makes stripe, as it is superfluid and solid at once, T, two symmetries, broken flow, and lattice. Our Raman lasers bend the energy landscape into two wells. I interfere both wells, and stripes appear P. Push it. The compression mode proves it is a real springy crystal E at the edge. That mode softens to 0, and the crystal melts stripe. And one question to leave you with. You now hold a crystal you can tune with a knob and squeeze on demand. Its stiffness dialed all the way down to 0. What would you build, what would you measure with matter like that?